Alright, today we are doing GM2b, Gaussian Malik, chapter 2, second video. We are continuing with graphical methods. And this figure, although not drawn to scale, represents 2.3a. So this is figure 2.3a of Gaussian Malik. We want to get some graphical or geometrical insight into solution of this problem. What is the problem statement? Let us first understand what's there in the problem. So first I'll just use a different color here. 1, 1, 1. These are fixed to the frame of the earth moving vehicle or earth moving machinery. Okay, so which I have not drawn, but it's sketched in the book. Alright. Here is a prismatic joint. Here is a prismatic joint. Other than that, there are several hinges, as you can see. This 2, 3 together is one hydraulic cylinder. 6 and 7 together is one hydraulic cylinder. And now that we have identified those, let me get rid of some of these extra drawings. Okay. Now this arm here, this one, all the way here, drawn in yellow, that is link 4. Link 4 has a point A here and this point O2, that is where the hydraulic cylinder acts. There is a point B here which is the pivot between body 4 and body 5. Body 5 is this green triangular part. Now here is another hydraulic cylinder. Here is a rigid link 8 which connects E and D, and this blue thing is the bucket whose position we wish to control. How many degrees of freedom does it have? If you count these as prismatic and you count the hinges and you count the number of links, where you count 2 and 3 as distinct, if you do this, you will find that it has 2 degrees of freedom. This means that this point D can go to any point in some region of the plane. The problem statement is D is to come to this point D prime. What is O7F and what is O2A? How much is the actuation in these actuators for D to come to D prime? If you think about it for a while, I suggest you pause the video and do that. You will realize that it's not that easy, but it can be done. So the way we proceed is like this. We notice that one thing that is very clear and simple is O2A is an actuator. It moves link 4 and link 4 is pivoted about O4. With that insight, I can take a radius from C to O4. I can draw an arc like this. C moves on this line. I'll say C arc just for clarity. Okay, so C moves there. What else do we know? We know that the distance from D to C being on this bucket is fixed. So the distance from D prime to C prime will similarly be fixed. Over here, centered at D prime, with that radius, I can draw an arc. I can draw a circle, and that circle will cut this at this point and this point. So these are two likely positions, two possible positions for C, but if you look at the arrangement of the bucket, I think you will agree that C prime is the logical location. So in any case, let us choose C prime as the logical location. Once we have chosen C prime as the logical location, we have located link 4. And the way I'm going to do it now for clarity is I'm going to use a fat pen and blue here and just draw it like this. So this is now link 4. I've identified the location of link 4. Using a protractor, for example, we can calculate this angle of travel, and using that same angle we can draw a line here and draw the same angle and so on, and in this way we can locate 4 as well. I'm sorry, point A as well, but for simplicity I will just say that this is now A prime and this here is B prime. Okay, so I've located A prime and B prime. You can also do this using tracing paper. So what you do is you take a tracing paper, you trace out this shape. Actually you just need to mark O4, A, B and C. Then you rotate the tracing paper so that O4 stays at the same place, C comes to C prime, and then you mark A prime and B prime. Okay, so now we've got A prime and B prime. What is the next thing we want to locate? Well, the next thing we want to locate is this triangle, which is body 5. We have located B prime. We could locate F prime or E prime. F prime cannot be located yet because it depends on the extension of this actuator, but E prime can be located because its distance from D is link DE, or the 8th link, which is fixed. And I know the new D prime, and I know the distance from E to B. So I come to B prime. Let me use red here. So I come to B prime, and then I take this distance here BE and I draw a circle. So I know that E is somewhere there. And then I also take the distance DE, I come to D prime and I draw another arc there which has the distance DE, and so this is E prime. Let me mark it in yellow here. This is E prime. How did I get it? I got it by an arc like this about B prime with the length BE, and an arc about D prime with length DE that located E prime. After I have located E prime and B prime, then I can locate F prime. Once I locate F prime, then I have got this length, and of course I had already located A prime, and therefore I have this length as well. And because I have located D prime and C prime, therefore with the tracing paper or otherwise I can draw the bucket, and so I can locate the bucket as well. So okay, that's a graphical solution. Let's do a different problem, and I will try to point out to you how sometimes things are less easy. So this is a 4-bar linkage that I am drawing now, but the coupler point is extended. So here is the input link, here is the coupler, but it is extended, and this is the coupler point P in which I am interested, and over here okay, so that's my 4-bar linkage. I ask the following question: if I take the input rod and rotate it by 30 degrees, where does P go? Where is P prime? This one is an easy problem. It's called a forward problem. This one is an easy problem. What I do is I know this length, so I draw an arc. I know this angle, so I draw a line. Where it cuts, if this point was A, this point here is A prime. Good. Let this point be B. Distance AB is known. Let this be O2 and let this be O4. this distance AB being known, from A prime I take that arc and I draw an arc. So B prime has to be on that arc, but of course the distance O4B is also known, so I draw another arc and it cuts here. So that now is B prime. Notice therefore that I have got A prime, I've got B prime, I can extend it in a straight line, and then as far beyond B prime as P was from B. A, B, P, one straight line, A prime, B prime, P prime, one straight line. If A, B, P was not straight, I could use a tracing paper. Okay, so in either case, here is P prime. Okay, so the forward problem is solved. How do I solve the reverse problem, the inverse problem? So for example, I may say, what is the rotation of the input link so that P reaches this point here, P double prime? Okay, now there's a problem. This is a single degree of freedom system. Because it is single degree of freedom, the point P will trace out a curve in this plane. Well, it has to pass through this point, apologies. It has to pass through this point, but it won't pass through this point in general if I choose an arbitrary point in the plane. So when I specify some point and say, will P pass through that point, typically it won't. However, if it passes through the point that is given, then what happens is PB is known, O4B is known, and in this way from here I can draw an arc at PB, I can draw another arc at O4B. This way I can locate B. Then from P I can extend B to wherever A is, and it is because of the constraint on the problem that the chosen point needs to lie on the correct curve that the distance O2A will be correct. If the input data is wrong, then it won't be correct, and such a motion will not be possible. Okay, so you can see that some of these problems are difficult. See, for example, suppose I want to find the leftmost point reachable by P. So this is just not possible graphically. We have to draw several positions, put a smooth graph, and get an approximate answer. Okay, so now with this motivation, we will move to analytical methods. In analytical methods, for planar problems, there are several rather lovely simplifications that are possible, and one of them is the use of complex variables. Complex variables, we work like this. We say, let this be a point A, let that be a point B, let this length be L, let x and y axes be given, let this be along x, let this angle be theta. Then the vector AB is written as equivalent to L e to the power I theta. So we are using complex notation to represent vectors in 2D. There are some advantages to doing things like this, and those advantages is what we turn to next. So we will consider the 4-bar linkage again, because that is an important case and many things are known about it. And then what we will do is we will think of this length as L1, this length as L2, this length as L3, this one as L4, this angle as theta 4, this angle as theta 3, this angle as theta 2. Then the vector L1 Real number, that means vector in the x direction, right? L1 plus L4 e to the power I theta 4 plus L3 e to the power I theta 3 minus L2 e to the power I theta 2 I theta 2. Let me clean it up. I theta 2 is equal to 0. Okay, so now this is a vector equation. It actually has two parts. Let me write them in blue. So there is the real part, which is L1 plus L4 cos theta 4 plus L3 cos theta 3 minus L2 cos theta 2 equals 0, and there is the imaginary part, which is L4 sin theta 4 plus L3 sin theta 3 minus L2 sin theta 2 is equal to 0. Okay, so we've got these two equations. What is given? Given L1, L2, L3, L4 and theta 2. Single degree of freedom, crank angle is given, input angle is given. So we want to find the configuration. That means all that remains to be found is theta 3 and theta 4. Two things are to be found, two equations are there. In principle, no problem. In practice also, this is a good, simple, well understood problem. And so what we do is we take, let me use green here and a slightly fatter pen. Let us look at this part. We can solve this equation for cos theta 3. We can solve this equation for sin theta 3. Then we get cos theta 3 square plus sin theta 3 square equals 1. That has the square of this one and the square of this one, but L4 square cos square theta 4, L4 square sin square theta 4, they add up, and so the cos square and sin square go away. Theta 2 is known, this is eliminated, and so we finally end up with an equation that has this form. We end up with an equation that has this form. Let me use a smaller pen here, not that much. Let me use yellow. So we have this form. We have A sine theta 2 theta 4 plus B cos theta 4 is equal to C, where A equals sine theta 2, B equals cos theta 2 minus L1 by L2, and C equals minus L1 by L4 cos theta 2 plus L1 square plus L2 square plus L4 square minus L3 square by 2 L2 L4. All right. Let me remind you that these are important equations. They are there in the book. I encourage you to read the book, but let me just mark them here so that we can refer to them later as and when we need them. So basically over here we eliminate theta 3, then we come here and we get this equation for theta 4. We could have eliminated theta 4 and got a similar equation for theta 3. You will see that if we exchange L3 and L4, we get very similar calculations, and we'll come to that. The equation we get is of this form. It's in the book. Read the book. A is this, B is this, and C over here is this. These expressions are there. It is a matter of just working through the symbols and getting the answer. I am not going to do it in detail. You can see the book. Very good. Okay, so now we can solve for theta 2, and it is easier. Theta 4. We can solve for theta 4. This equation is to be solved. Let me mark it in red and put it here. This equation is to be solved for theta 4, and the way we do it, to avoid some false solution branches which we would then have to eliminate, the way we do it is we use this identity. So we write sine theta 4 is equal to 2 tangent of theta 4 by 2 over 1 plus tan square theta 4 by 2. And similarly, cos theta 4 is equal to 1 minus tan square of that same thing, theta 4 by 2, over 1 plus tan square of theta 4 by 2. See the book. When we do this, then we get a further simplification. Okay, and the simplification is like this. We end up with this gives something times tan square theta 4 by 2 plus something times tan theta 4 by 2 plus something equals 0. This is a quadratic equation in theta 4. Move to yellow for emphasis. This gives us theta 4 has now two roots. Theta 4 is equal to, and we have 2 tan inverse a minus plus square root of a square plus b square minus c square, the whole thing by b plus c. These are the two roots. Now theta 3 also gives similar results. So there are similar results for theta 3. Okay, and here for theta 3, for L3 and L4 are to be exchanged, as you can see in these equations. Here you see in these equations, L3 and theta 3, L4 and theta 4 appear in this combination, right? So very, very similar. So what Ghosh and Malik's book points out, small apology, minor apology, here I mean L3 and L4 are interchanged, but also plus minus. So theta 4 1 will correspond to theta 3 1 if I take the minus sign here and the plus sign in the other expression. Read the book. Okay, all right. So we've made some progress. Now rest of this lecture is to see how theta 4 varies against theta 2. And we have formulas, we just have to put them in. So we will now move to MATLAB and make plots. So I have MATLAB open and I have code here, and this code is a bit long, but don't worry. Let us look at these lengths. So let us go back here and let us now okay, so let us look at a Grashof linkage. Okay, so let us take this to be 7, let us take this to be 2, let us take this to be 6, and let us take this to be 4. Okay, so 2 plus 7 is less than 4 plus 6. This is a Grashof linkage. Okay, now I mean this 2, 6, 4 and 7 are not numbers, they are dimensions, right? Okay, very good. So now let's do different fixities, right? So let us take green and let us say 7 is fixed. So if we fix this one, then L1, L2, L3, L4 are 7, 2, 6, 4, and this is a crank and this is a rocker. Clear? Good. 7, 2, 6, 4, Grashof crank rocker. Let us go here. Let us go here. 7, 2, 6, 4, Grashof crank rocker. Okay, I have to be in the right directory. Okay, what am I doing here? Theta 2, I'm going from 0 to 2 pi. It's a crank. Theta 2 goes all the way around the circle. A is sine theta 2, B is cos theta 2 minus L1 over L2. We can check our formulas, they are here somewhere. So we can check our formulas. A is sine theta 2, B is cos theta 2 minus L1 by L2. C is minus L1 by L4 cos theta 2 and something over here. Look, that's what we have here. C is minus L1 by L4 cos theta 2 and so on. So this is matching. Okay. Now T41, I have that 2 arctangent, right? So I have 2 arctangent. I have written it here. Let me see. It should be here. 2 arctangent, and then I have the minus. So that's what I have here in my MATLAB code. 2 arctangent with a minus. This part of the code ignore for the moment. We will come back to it. This part of the code ignore for the moment. Okay. Now I have T42, same thing, it is just the other one, so it is plus. Okay, remember I have a crank rocker. Why do I have 2 solutions? Similarly, there is some other code here, don't pay attention, we are just plotting. Okay, so let's go back. We have a crank rocker. When we have a crank rocker, let me see here. Remember that there are actually 2 modes of assembly. So I also have this mode of assembly. That is why I will have one theta 4 which is between 0 and pi, and I will have another theta 4 that is more than pi but less than 2 pi. Okay, very good. Let's come back here, go back to MATLAB, and let's see, run this program, and it's giving me some. This is an instantaneous jump. Okay, so this is an instantaneous jump. I don't know why it is doing that, but if I plot it like this, if I plot it with just dots, then I should not have this difficulty. See, it's just this one curve. So from end to end it has come here for some reason, but it's not a problem. This is really what the curve is like. So let me just change this to this one, and then it should be all right. Okay, so these are the two curves. One is from pi to between 0 and pi, and the other is between pi and 2 pi. Okay, so this is theta 4. You can see that theta 4 is rocking. There are two assemblies, and theta 2 goes from minus pi to pi. Oh, that's why I was having this trouble. I made theta 2 go from minus pi to pi. Apologies. I can do this here. I should be able to comment it out. Well, don't worry. There was comment, right? Let me comment this out. Okay, so then it will not have this problem. I will come to the importance of that. Now you see it is going from 0 to 2 pi, and there is just no difficulty. Okay, all right. What happens if we use the same linkage but in a different setting? So instead of fixing this link, suppose we fix this one. Now it is a double rocker. Sorry, double crank. Now it is a double crank. Which is it? Double rocker. Sorry, if I fix this one, it is a double crank. My apologies. So if I fix this one, then it is a double crank. Fix this, you get a double crank. So that means 2, 6, 4, 7, we should get a double crank. Okay, we will come here. I will come here, and I will say 2, 6, 4 and 7, and it should be a double crank. You see, it's a double crank. It is going up from some value to 2 pi, then again it is being set to 0, and then it is going from here. Otherwise it would have gone there, it would have been outside the 0 to 2 pi range. This is why this line was there. Now let me explain what we are doing here. The command any in MATLAB has a very simple role. Let us say a is equal to zeros 3. Okay, so every single element of the matrix A is 0. If I say any A, it checks in each column and tells me whether there are any non-zero elements. It's a binary variable, so all zeros, because there is nothing non-zero here, there is nothing non-zero here, there is nothing non-zero here. Suppose I make this element 0, or maybe I'll make this element not 0. So I have A 2, 3 is equal to minus 0 point some number. Okay, so that is not 0. Now if I say any in A, it will return 1 here, because in this column there is something not 0. Okay, but if I have a row vector or a column vector, then it just gives one number. So if A is equal to zeros 1, 8, okay, so any of A will give me 0. But if I say A of 7 is equal to 0.2, then any of A will give me 1. If I say A of 4 is equal to minus 0.3, so now two elements are not 0, any of A will still give me 1. Okay, so that's what any does. It just sees if anything is not 0. Okay. So with that knowledge, let us come here. If any of theta 4 1 is more than 2 pi, then I will subtract 2 pi, but not from everything, only from those places where it is more than 2 pi, because this itself is a binary variable. Think about this code, you will understand what it is doing. Meanwhile, if any of theta 4, which I am calling temp, is less than 0, then I add 2 pi. And after this process is over, I reassign this temp back to T41. Same here. Okay. Alright, so that is how this line we still have not seen. Sorry, not that. This line we still have not seen, and I will come to that next. So that is how when it crosses 2 pi, it comes back here, and then it continues like this. Okay, so you can see that both, it is a double crank. Okay, it's a double crank. All right, now let us do a double rocker. So if we do double rocker, what we have to do is we have to fix this one, and that means it has to be 4 7 2 6, and that's a double rocker. Okay, so when I take a double rocker, there is going to be one problem which you can anticipate, but we will 4 7 2 6. Okay, there's going to be a problem. What is the problem? The problem is that before we take the tan inverse, we have to take a square root, and this, if this square root is of a negative number, then theta will be complex. Okay, so if it is complex, that means there is no physical solution. It's a double rocker. Theta does not go all the way from 0 to 2 pi, right? So we know that there will be theta 2 values which I will try, and what I will get is theta 4 will turn out to be complex. And so when in my MATLAB code, what I have done is I have just put a simple check here. So I have said imaginary part of theta 4 is 0. So wherever it is real, this is going to be 1. I am taking imaginary part and dividing my 1. Imaginary part is 0 anyway, so I am not changing anything. But where the imaginary part is 0, there, where the imaginary part is not 0, I am sorry, so this is a non-zero number, but over here the logical variable returns 0, so this becomes infinite, so nothing will be plotted. Okay, so should be all right. Let us see. Okay, so it is complaining, it is warning you that some complex things have been ignored, but let us look at the picture. And you see it has two different loops. Why is it two different loops? Because this is a Grashof mechanism. It does not switch to the two assemblies. Let me explain. So it is a double rocker, and there are two modes of assembly. So I come here, this is the one I fixed. Okay, so let me show it here itself. Okay, let me show it with a blue pen, but with a fat pen. Okay, so here this is fixed, and this is one mode of assembly, but there is another mode of assembly like that, and you can see that this will rock here, this will rock here, and this will rock, this will rock, but this assembly will not be able to go over to that assembly. In Grashof mechanisms, you can't go from one assembly to the other. That is why in this MATLAB figure, which I can put here, in this MATLAB figure you can see that there are two modes of assembly, and each is a rocker. So theta 2 can only go from here to here. During that, theta 4 can only go from there to there. Okay, good. Let's do a non-Grashof. Okay, so for a non-Grashof, we have to just figure out what to use. Let's see. Non-Grashof, all non-Grashof mechanisms are double rockers, so that part of it is not a problem. Let's try 7, 4, 5, 5. So that's non-Grashof. I can fix this, it doesn't matter. So then my inputs are 7, 4, 5, 5. Smallest and largest, 4 plus 7 is bigger than 5 plus 5. So this is a non-Grashof and it's a double rocker. Okay, 7, 4, 5, 5. So I come here, I go back to my MATLAB code and I have 7, 4, 5, 5 non-Grashof. Okay. Here's the figure. And it seems like there are two branches, but actually you see this one is reaching 2 pi and then this one is again on this side of 0. So actually this part can be moved here, and that a simple way to do it is if it is bigger than pi, then we can subtract 2 pi. Okay, something like this. So that is how we have to change the code, and we have done that. That is the last part of the code is here, which I will now uncomment. Not comment, not comment. That's what I want. So now if it is more than pi, then I subtract 2 pi, and if it is less than minus pi, I add 2 pi at the same locations. And you see now it forms this single closed loop. This is because a non-Grashof mechanism switches its assembly. Okay, so let me try to explain. This is a non-Grashof mechanism. So let me take blue here now. 7 and 4 is 11, 5 plus 5 is 10. Therefore some position like this will come where this will be straight, and from that is the extreme position of this link. However, this has a choice. Okay, so it can go, when this link returns, this can go to this assembly or it can go to that assembly from that straight position. That is why both assemblies are accessible to the non-Grashof mechanism, and so when you have a double rocker, it will look like this. These pictures, qualitatively similar pictures, are given in your book, but here we have plotted them using MATLAB. Then that is all for today. Thank you.